Yogah Karmasu Kaushalam.
Good morning everyone. I am Nikita Mishra from Department of Chemistry, Gujarat University. Welcome you all in the online refresher course in chemistry hosted by Department of Chemistry, Gujarat University, Ahmedabad. On behalf of Dr. Jagdish Joshi, Professor, Director, UGC HRDC, Gujarat University, and Dr. Dilip Vasawa, Assistant Professor, Refresher Course Coordinator, HRDC, Department of Chemistry, Gujarat University. I welcome you all in the session of Dr. Paresh Patel, MSc PhD, Associate Professor, Veer Narmad South Gujarat University, Surat, Gujarat. His specialization in academics, organic chemistry, reaction mechanism, pericyclic reactions, photochemistry, natural products, rearrangements, and molecular symmetry. In research field, his specialization is synthetic organic chemistry, dyes, drugs, and polymers. He has supervised 7 PhD scholars and 1 MPhil. He has 1 UGC major project and 51 publications in various national and international journals. He has delivered 8 invited talks in various webinars, workshops at different platforms. He has membership of scientific bodies like member of Board of Studies, School of Sciences, PP Savni University, Kosamba, Surat. Member of Board of Studies, Veer Narmad, South Gujarat University, Surat. Life member Indian Chemical Society and life member Indian Council of Chemists. Thank you.
Respected the Director of UGC HRDC of Gujarat University, Professor Jagdish Joshi sir, respected Coordinator of the third online refresher course, Dr. Dilip Vasawa sir, and dear participants. Today we are going for the discussion on molecular symmetry. We know that the beauty of all the natural things is due to the symmetry, and that type of the symmetry arises in our molecule, so that can be recognized as molecular symmetry. Or we can say the correspondence of a figure with reference to plane, line, or point of a symmetry. Thus, a circle is symmetrical about any diameter. The term symmetry has become synonyms to the beauty because the nature has made most of its creation symmetrical, as for example, the sun, planets, animals, and plants. Scientifically speaking, an object is said to be symmetrical if it can take up more than one equivalent orientations. So as for example, if we take hydrogen molecule and if we image one imaginary axis on the hydrogen molecules to get the equivalent orientation position. So that is the examples of the molecular symmetry. We know that symmetry is all around us and is fundamental property of natures. All the natural things are so beautiful and due to the symmetry. This is the examples of Taj Mahal, and the beauty of this Taj Mahal is due to its symmetry. And this is Eiffel Tower, and this is also beautiful, and this beauty is due to the symmetry. Symmetry is an object has 2 or more equal sides when split in half or in smaller pieces. So this is the symmetry in nature. This is butterfly, and butterfly is so beautiful and due to its symmetry. Now, 2 important terms are most important in our molecular symmetry. First one is symmetry elements, and second one is the symmetry operations. Okay, what are symmetry elements? Plane, line, or point. These are known as a symmetry elements, and the process is carried out on either plane, line or point to get the equivalent orientation position. This process can be recognized as symmetry operations. So repeat again. Plane, line, or point. These are known as a symmetry elements. And the process is carried out on either plane, line, or point to get the equivalent orientation position. This process can be recognized as symmetry operation. Now, symmetry elements and their related symmetry operations can be classified into identity, proper axis of rotation, mirror planes, center of symmetry, and improper axis of rotation or rotational reflection axis of symmetry. Now, first symmetry element is identity. E means it is meant. It means unity. Each and every molecule consists identity symmetry elements. And if we operate identity symmetry operation on any molecules, molecule remains unchanged. There is no change in the position of the molecules. So first element is identity, and if we operate identity symmetry operation on molecule remains as fixed. Second symmetry element is proper axis of symmetry, and this symmetry element can be recognized as Cn, where n is equal to order of axis. And order of axis can be represented by n is equal to 360 by theta. Okay. In case of hydrogen molecule, we already discussed, if we rotate the hydrogen molecules along the imaginary axis around 180 to get the equivalent rotation position. But let us start. What is proper axis of symmetry? We have to image a line or axis, and with the help of that axis, if we rotate our molecules along the axis to get the equivalent orientation position. So this type of the symmetry can be recognized as proper axis of symmetry. And this symmetry element can be designated by capital C and small n Cn, where n is equal to order of axis. If we rotate the molecules around 180, so n is equal to 360 by 180, so n is equal to 2. In case of the water molecule, if you rotate water molecules along the imaginary axis around 180 to get the equivalent orientation position, it means in case of the water molecule, n is equal to 2. In case of the ammonia molecules, if we rotate the ammonia molecules along the imaginary axis around 120 to get the equivalent rotation position. So in that case, n is equal to 3. Cyclobutane, if we rotate cyclobutane along the imaginary axis around 90 to get the equivalent orientation position. So order of axis for the cyclobutane molecule is equal to 4. Similarly, if we go for the rotation of the imaginary axis in benzene, so we have to rotate benzene molecule on that imaginary axis around 60 to get the equivalent orientation position. So n is equal to 360 by 60 is equal to 6. Similarly, if we go for the infinite times of the rotations, so anyhow, Cn can be recognized as a symmetry element. And if you go for the symmetry operation, so that can be designated as Cnk. So K represents numbers of time that symmetry operations. Now, these are the imaginary axis in case of the water molecule and ammonia molecules. Okay. Now, in case of the water molecules, this is oxygen and these two are the hydrogens. Okay. Now, this one is the imaginary axis, and with the help of this axis, if we rotate these molecules around 180 to get the equivalent orientation position, it means here n is equal to 360 by 180. It means n is equal to 2. In case of ammonia molecules, and we know that shape of ammonia molecule is a pyramidal. Okay. Now, if we image a axis, just like this one. And if we rotate these molecules along this imaginary axis around 120 to get the equivalent orientation position. So in case of ammonia molecules, n is equal to 360 by 120. It means n is equal to 3. This is the rotation in case of the water molecules. Okay, if we rotate these molecules along this imaginary axis to get the equivalent orientation position. This is the trichloroplanar molecules. Example is the BF3 molecules. Okay, and we know that BF3 molecule is a planar molecule. This one is the imaginary axis, and with the help of this imaginary axis, if we rotate these ammonia molecules along the imaginary axis around 120 to get the equivalent orientation position. So the order of axis in case of this imaginary axis is 3. So this symmetry element can be recognized as a C3. Now, in case of BF3 molecules, if we rotate this molecule along the another imaginary axis around 180 to get the equivalent orientation positions. So this can be recognized as C2. Why C2? If we rotate this molecule along this axis around 180 to get the equivalent orientation positions. Similarly, this is the another imaginary axis, and with the help of this imaginary axis, if we rotate these molecules along this axis around 180 to get the equivalent orientation position. Similarly, over this is the fourth imaginary axis, and with the help of this imaginary axis, if we rotate these molecules along this axis around 180 to get the equivalent orientation position. So in case of BF3 molecules, one C3 axis of symmetry and 3C2 axis of symmetry, and C3 is perpendicular to 3C2. Now, which one is the main principal axis? According to the rules and regulations of the molecular symmetry, higher order proceed first as a main principal axis. So in case of BF3 molecule, there is no questions about the C3 and C2. The order of axis of C3 is higher than C2. So main principal axis can be recognized as C3. So we have to proceed the higher order of axis proceed first. Now, in case of order of axis are the same, then we have to choose the which one is the main principal axis. So in that case, we have to consider the axis passes through numbers of maximum atoms that can be considered as a main principal axis. So in case of the BF3 molecules, 1C3 and 3C2s are perpendicular to the main principal axis C3. Now, this is the C4 axis of rotation in cyclobutane molecule. And we know that the shape of the cyclobutane molecule, just like this one. This one is the imaginary axis. And with the help of this imaginary axis, if we rotate these molecules around 90 to get the equivalent orientation position. So in case of the cyclobutane, n is equal to 360 by 90 is equal to 4. So order of axis in case of the in the cyclobutane is equal to 4. So symmetry element is a C4. And next one is cyclopropane molecule. In case of the cyclopropane, if we rotate this molecule along the imaginary axis around 72 to get the equivalent orientation position. So order of axis in case of the cyclobutane is 5. So symmetry element can be recognized as a C5. Now, in case of the cyclopentane, main principal axis is C5. Why? The order of C5 is more than C. In case of the cyclopentane or cyclopentadiene, 5 C2s are present. Why? if we rotate these molecules along the any one C2 to get the equivalent orientation position. Or we can say if we rotate these molecules around 180 to get the equivalent orientation position. So 1 C5 is present in the cyclopropane and 5 C2s are perpendicular to the main principal axis. Now C6 axis of rotation in benzene molecule. In case of the benzene, if we image this imaginary axis and if we rotate these molecules along this axis around 60 to get the equivalent orientation position. So the main principal axis is C6. In case of the benzene molecules, C6 is perpendicular to 6 C2s. And these are the position of the C2s. Now, what is the meaning of the C2? If we take this imaginary axis and if we rotate these molecules along this axis around 180 to get the equivalent orientation position. So benzene molecule consists 6 C2s and C6 is perpendicular to 6 C2s. Now, symmetry operations. We know that BF3 molecule consists of C3 as a main principal axis. And if we rotate these BF3 molecules along the imaginary axis around 120 to give one orientations. So this boron-fluorine bond will come over here by rotating 120 along the main principal axis. Okay, if you go for the another 120 rotation, so this boron-fluorine bond will come over here. So these symmetry operations can be recognized as a C31 and second time rotations can be represented as a C32. So repeat again. In case of the BF3 molecules, one C3 is a main principal axis and 3 C2s are the axis of rotations are present in the BF3 molecules. Now, if you go for the symmetry operations, that is rotation along this imaginary axis around 120 to give equivalent orientation position. So in this equivalent orientation position, this boron-fluorine bond will come over here and this is the first time rotation. So this can be represented as C31 or C3 plus. It means this symmetry operation can be represented as C31 or C3 plus. If you go for the another 120 rotation, so this boron-fluorine bond will come over here. So this symmetry operation can be recognized as C32. And in case of the BF3 molecules, we know that these are the main principal axis C3, and if we operate difference, if we operate C3 symmetry operation on the BF3 molecule to give this equivalent orientation positions. So in case of the BF3 molecules, C3 is perpendicular to 3 C2. In case of the BF3 molecules, we already discussed. This is NiCN4-2 complex. In case of the NiCN4-2 complex, this one is the imaginary axis is C4. Why C4? If we rotate these molecules along this imaginary axis around 90 to get the equivalent orientation position. So order of axis in case of the NiCN4-2 complex is 4. So this symmetry element can be recognized as C4. In case of the benzene, this one is the imaginary axis. And if we rotate these molecules along this imaginary axis around 60 to get the equivalent orientation position. So order of axis in case of the benzene is 6. So symmetry element can be recognized as C6. Now, if you go for the symmetry operation, C61, C62, C63, C63 to get the another equivalent orientation position. Now, in case of BF3 molecule, we already discussed that 3 C2s are perpendicular to the main principal axis. In case of the NiCN4-2 complex, 4 C2s are perpendicular to the main principal axis. And in case of the benzene ring, C6 is perpendicular to 6 C2s. That is, we already discussed. Now, in case of the PTCl4 minus 2 complex, this one is the main principal axis. In case of the PTCl4, this one is the main principal axis. Why? The order of this axis is higher than remaining. So if we rotate these molecules along this axis around 90 to get the equivalent orientation position. Now, if we rotate these molecules along the another imaginary axis around 180 to get the equivalent orientation position. So in case of the PTCl4 minus 2, main principal axis is C4 and C4 is perpendicular to 4 C2s. These are the another C2s are present in the PTCl4 minus 2 complex. Now this is the most interesting example. That is iron pentacarbonyl. In case of the iron pentacarbonyl, the shape of this molecule is trigonal bipyramid. In case of the iron pentacarbonyl, this one is the imaginary axis. And with the help of this imaginary axis, if you rotate these molecules around 120 to get the equivalent orientation position. So this type of the molecular symmetry can be recognized as a rotational axis of symmetry, and order of axis in case of the FeCO5 is 3. So symmetry element can be recognized as C3, and symmetry operations can be recognized as C31, C32, C33. These are the symmetry operations. Now, third symmetry element and the related symmetry operations is plane of symmetry. Plane of symmetry can be designated by sigma. Now, plane of symmetry can be classified into 3 categories. First one is mirror plane containing principal axis of rotation. It means a plane is parallel to main principal axis. So that type of the plane of symmetry can be recognized as sigma V. Now, what is plane of symmetry? If we image a plane or mirror, and with the help of that mirror, we can bisect the molecule in such a way that one part is the mirror image of the another part of the molecules. So that type of the symmetry can be recognized as plane of symmetry. Now, plane of symmetry can be categorized into 3 categories. So first one is vertical plane of symmetry, and that can be recognized as sigma V. In case of the vertical plane of symmetry, if plane is parallel to main principal axis, so that type of the plane of symmetry can be recognized as vertical plane of symmetry. Second category is horizontal plane of symmetry. In case of the horizontal plane of symmetry, if plane is perpendicular to the main principal axis, so that type of the symmetry can be recognized as a horizontal plane of symmetry. And third one is dihedral or diagonal plane of symmetry. Now, in case of the diagonal plane or dihedral plane of symmetry, imaginary plane which can bisect the main principal axis as well as C2 in such a way that one part is the mirror image of the another part of the molecule. So this type of the plane of symmetry can be recognized as dihedral or diagonal plane of symmetry. Now, first example, first category of the plane of symmetry is vertical plane of symmetry. This is the water molecule. In case of the water molecules, this is the C2 main principal axis, and water molecule consists 2 vertical planes. Why these are the vertical planes? Now, what is vertical plane of symmetry? If plane is parallel to main principal axis, so that type of the plane of symmetry can be recognized as vertical plane of symmetry. Now, in case of the water molecules, water molecule consists 2 planes. Now, this is first plane and this is second plane. This plane can be recognized as sigma V YZ plane. Why this is sigma V YZ plane? because this edge is parallel to z-axis and this edge is parallel to y-axis. It means this plane can be recognized as sigma v yz plane, and the pink colored plane can be recognized as sigma v xz plane. Sigma v xz plane. Why sigma v xz plane? This edge is parallel to z-axis and this edge is parallel to x-axis. So this plane can be recognized as sigma v xz plane. Water molecule consists two vertical planes. Why two vertical planes? Both these planes are parallel to main principal axis. So both these planes are vertical planes. One plane, that is gray colored plane, can be recognized as sigma v yz plane, and pink colored plane can be recognized as a sigma v xz plane. So water molecule consists two vertical planes. And if you go for the symmetry operations on water molecule, then what will happen? In case of, if we operate sigma v yz, symmetry operation on water molecule, which can bisect the molecule. If we operate sigma v yz symmetry operation on water molecule to change the position of hydrogens, why this plane is bisect the molecule in such a way that one part is the mirror image of the another part of the molecules. So if we operate sigma v yz to get the equivalent orientation position, or we can say to change the position of the hydrogens. This is the pink colored plane, and this pink colored plane can be recognized as sigma v xz plane, or this can be recognized as molecular plane. So if we operate sigma v xz symmetry operation on molecule, molecule remains as it is. There is no change. Why? This is known as a molecular plane. So we have to remember that if we operate sigma v yz plane to change the position of the hydrogens, but if we operate sigma v xz, there is no change in the position of the hydrogens. So this is the first examples of the vertical plane of symmetry. This is the ammonia molecule, and we know that the shape of the ammonia molecule is pyramidal, and this is the imaginary axis as a C3, and we know that ammonia molecule consists three vertical planes. Why these are the vertical planes? All the three planes are parallel to main principal axis. So all the three planes are the sigma v planes. So ammonia molecule consists three vertical planes that can be recognized as a sigma va, sigma vb, sigma vc, or sigma v1, sigma v2, or sigma v. So these are the symmetry elements. But if you go for the symmetry operation, so if you operate any symmetry operations, sigma Va on the ammonia molecule, so what will happen? So there is no change in the position of the first hydrogen, but there may be the change in the position of the hydrogen 2 and hydrogen 3 by operating sigma V symmetry operation. So that can be recognized as a symmetry operation as a sigma V. Now, second type of the plane of symmetry can be recognized as a horizontal plane of symmetry, and horizontal plane of symmetry can be designated by sigma h. Now, in case of the BF3 molecule, this is the imaginary axis, and with the help of this imaginary axis, if we rotate this molecule along this axis around 120 to get the equivalent orientation position. BF3 molecule consists main principal axis is a C3, and 1, 2, and 3 C2s are perpendicular to the main principal axis. Now, what is horizontal plane of symmetry? If plane is perpendicular to the main principal axis, so that type of the plane of symmetry can be recognized as horizontal plane of symmetry. In case of the BF3 molecules, this one is the main principal axis, and this plane is perpendicular to the main principal axis. So this type of the plane of symmetry can be recognized as horizontal plane of symmetry. This is the another examples of the horizontal plane of symmetry. This is PF5 molecules, phosphorus pentafluoride molecules. In case of the PF5 molecule, the shape of this molecule is trigonal bipyramid. In case of the PF5 molecules, this one is the imaginary axis, or we can say this is the principal axis, and the order of this main principal axis is C3. And if we rotate these molecules along this axis around 120 to get the equivalent orientation position, and 3 C2s are perpendicular to the main principal axis, and this plane is perpendicular to the main principal axis. So obviously, if the plane is perpendicular to the main principal axis, so that type of the plane of symmetry can be recognized as horizontal plane of symmetry. Third type of the plane of symmetry is diagonal plane of symmetry, and it is designated by sigma d. Now, what is diagonal plane of symmetry? We have to image a plane which can bisect the main principal axis and C2 in such a way that one part is the mirror image of the another part of the molecule. So that type of the plane of symmetry can be recognized as diagonal plane of symmetry. This is alane molecule. And in case of the alane molecule, this one is the main principal axis. This is C2. This is also C2. And if we image a plane in just like this one, which can bisect the main principal axis and C2 in such a way that half of the molecule is mirror image of the another part of the molecule. So this type of the plane of symmetry can be recognized as diagonal plane of symmetry. Now, these are the examples of the plane of symmetry. Benzene molecules. Obviously, we know that benzene can be considered roughly as a planar structure, and this plane is perpendicular to the main principal axis C6. So this is an example of sigma H. Water molecule we already discussed. Now, fourth type of the symmetry element, fourth symmetry element is center of symmetry. Center of symmetry can be designated by small I. Now, this is an imaginary point in the molecule, in the center of the molecule, through which the reflection of the each atom can be carried out to result in its coincidence with the equivalent atom. It means in case of the center of symmetry, we have to find out, or we have to image a point, and with the help of the point, we can inversify each atom of the molecule to that point to get the equivalent orientation position. So that above the symmetry can be recognized as center of symmetry. Now, this is the examples of octahedral complexes. In that, this is the imaginary point, and with the help of this imaginary point, we can inversify each atom of the molecules. So this type of the symmetry can be recognized as center of symmetry. So this is the center of symmetry in case of benzene ring, and this is the imaginary point in case of the trans dichloroethylene. Now, next, symmetry elements and the related symmetry operation is improper axis of symmetry or rotational reflection axis of symmetry, and this can be designated by Sn as a symmetry elements, and symmetry operation can be designated as Sn1, Sn2, Sn3, etc., or we can say Snk. K represents numbers of time that symmetry operation. Now, what is improper axis of symmetry or rotational reflection axis of symmetry? This is an imaginary axis and passing through the molecule. And if we rotate any molecules around theta and reflection through horizontal plane, it means horizontal plane, it means it should be perpendicular to the main principal axis to get the equivalent orientation position. So this type of the symmetry can be recognized as rotational reflection axis of symmetry or improper axis of symmetry. Repeat again. This one is the imaginary axis. And with the help of this imaginary axis, if we rotate molecules around theta and reflection through horizontal plane of symmetry to get the equivalent orientation position. So this type of this symmetry can be recognized as rotational reflection axis of symmetry or improper axis of rotation, improper axis of symmetry. And this can be designated by S and K. N represents order of axis and K represents numbers of time that symmetry operations. Now, this is the improper rotation in tetrahydral. So in case of tetrahydral, just like a methane molecule, if we rotate these molecules along this axis around 90, and then reflection through this plane to get the equivalent orientation position. So this is the improper axis of rotation in case of the tetrahedral structure. So I think these are the 5 symmetry elements and symmetry operations. First one is identity, and identity can be designated by capital E. And if you operate identity symmetry element, symmetry operation on a molecule, molecule remains unchanged. There is no change in the position of the molecules. Second symmetry element is proper axis of symmetry, and that can be designated by C and K. N represents order of axis, and K represents numbers of time that symmetry operation. N is equal to 360 by theta, and with the help of that this equation, we can derive the order of axis for that molecule. And symmetry operations can be designated by C and K. K, it means how many types of the symmetry, numbers of the times symmetry operations. Okay, so if you go for the first time symmetry operation, that can be designated as Cn1. Second time Cn2, Cn3, etc. Then third type of the symmetry operation is plane of symmetry. In plane of symmetry, we have to image a plane, and with the help of that plane, we can bisect the molecule in such a way that one part is the mirror image of the another part of the molecule. Plane of symmetry can be categorized into 3 categories. First one is vertical plane of symmetry. Second one is horizontal plane of symmetry, and third one is diagonal or dihedral plane of symmetry. In case of vertical plane of symmetry, if plane is parallel to main principal axis, so that type of the plane of symmetry can be recognized as vertical plane of symmetry. If plane is perpendicular to the main principal axis, so that type of the plane of symmetry can be recognized as a horizontal plane of symmetry. And imaginary plane can bisect the main principal axis and C2 in such a way that one part is a mirror image of the another part of the molecule. So that type of the symmetry can be recognized as a dihedral plane of symmetry. The next is the center of symmetry. We have to image a point, and with the help of that point, we can inversify the each and every atom of the molecule. So that can be recognized as a center of symmetry. And last symmetry elements and their related symmetry operations, that is rotational reflection axis of symmetry or inversion of symmetry. Inversion of symmetry can be designated by S and K. N is equal to order of axis, and K represents numbers of time that symmetry operations. Now, what is improper axis of symmetry? We have to rotate the molecules around theta and reflection through horizontal plane to get the equivalent orientation position. So this above the symmetry can be recognized as a improper axis of symmetry. Now, second title of our today's discussion is point group. How to find out the point group of any molecules? We know that what is point group? Point group is nothing but the collection of symmetry elements or the related symmetry operation which meet a point is known as a point group. Now, according to the Schoenfeld's method, we can designate point group to the any molecules. With the help of this chart, we can assign a point group to that molecules. So first question, is a molecule linear or non-linear? If it is linear, then C infinite V or D infinite H point group may be present. If sigma V is present, so C infinite V point group may be present. If sigma H is present, then D infinite H point group may be present. So this is the case in case of linearity. If our molecule is non-linear, then we have to make a question. Any multiple higher order axes are present. Now, what is the meaning of the multiple higher order axis? Multiple, it means minimum 3 multiple is required, and order, minimum order is 3. It means 3C3 is the minimum criteria to be a multiple higher order axis. If multiple higher order axes are present, then point group may be TD, OH or IN. If sigma D is present, then TD point group may be present. If sigma H is present, then point group may be OH. Both are absent, then point group may be IN. TD means tetrahydral, OH means octahydral. Now, multiple hard or axes are absent. Then we have to go for the any proper or improper axis of symmetry, present or absent. If there is no proper and improper axis of symmetry is present, then point group may be C1, CS or CS, CI or C1. If sigma H is present, then point group is CS. If I is present, then point group may be CI. Both are absent, then point group may be C. Now, improper axis is present, then that can be designated by SF. Now, in case of the proper axis, we have to make a question. CN is perpendicular to NC2. If yes, then we have to go for the D option. Otherwise, we have to go for the C option. In case of the both these cases, if H is present, then we have to go for the sigma H is present. Then point group may be DNH in case of the D case. If sigma V is present, then DNV present, and sigma D is present, then DND point group may be present. And in case of the C option, if sigma H is present, then point group may be CNH. Sigma V is present, then CNV, and sigma D is present, then CND. All are absent, then point group may be CN. So with the help of this chart, we can assign a point group to the molecules. Dear participants, now we are going for the how to assign a point group to the molecules according to the Symmetry method. So let us start with the point group. Point group is may be defined as a collection of different symmetry elements and their related symmetry operation which meet a point is known as a point group. Now we have to follow a chart, and with the help of the chart we can assign a point group to the molecules. So first question, is a molecule linear or non-linear? Is a molecule linear or non-linear? And non-linear. If our molecule is linear, then there is no questions regarding the C infinite V in and D infinite H point group may be present. Now, in this one, sigma V is present, then C infinite V point group may be present. And sigma H is present, then D infinite H point group may be present. So, dear participants, first of all, we have to make a questions that molecule is a linear or non-linear. If linear, then C infinite V or D infinite H point group may be present. If sigma V is present, then point group can be assigned as a C infinite V. And if sigma H is present, then D infinite H point group may be assigned. If it is non-linear, then non-linear, then we have to make equations. Any multiple higher order axis are present. If yes, then TD and OH point group may be present. Then we have to go for the sigma H is present, sigma V is present, then TD. Sigma H is present, then OH point group. Both are absent. Then no any proper or improper axis of rotation. No. Yes. Improper. Then acid. Proper axis. C1, CS, and C. So, dear participants, this is the chart, and we have to follow this chart. And with the help of this chart, we can assign a we can assign the point group to the any molecule. So, first one is a molecule linear or non-linear? Okay, if it is linear, then C infinite V or D infinite H point group may be present. If non-linear, then we have to make another questions. Okay, if it is linear, then C infinite V or D infinite H point group may be present. Okay, sigma V is present, then point group can be assigned as C infinite. If sigma H is present, then point group can be assigned as a C D infinite H. Now, if molecule is non-linear, then we have to make up another questions. Any multiple harder axes are present. Now, what is the meaning of multiple? Multiple, it means suppose 3C4, 4C4, 3C3. So 3, 4, 3. This can be recognized as a multiple. And higher order it means 4, 4, 3. So these are known as a higher order. So minimum criteria to be a multiple hard order axis is 3C3. Okay. So if our molecule consists three multiple and three higher order of axis is three, then multiple higher axes are present. Now, in case of multiple higher axes are present, then sigma V, sigma D, and ion point group may be present. If our molecule consists sigma V, then point group is D. If sigma H is present, then point group is 2H. And both are absent, then ion point group may be assigned. Now, if multiple harder axes are absent, then we have to go for the next question. Any proper or improper axis of rotations are present? If no, then C1, CS, and CI point group may be present. Now, how to separate C1, CS, and CI? If sigma is present, then point group is CS. If I is present, then point group is CI. Both are absent, then point group is C1. Now, if any proper or improper axes are present, if improper axes are present, then point group can be assigned as a assign. And in case of the proper, we have to make a question. Cn is perpendicular to NC2. Yes. Then we have to go for the D option. Otherwise, we have to go for the C option. In case of the D option, first question, sigma is present, then DNS point group may be present. Sigma V is present, then DNV point group may be present. Sigma D is present, then point group may be DND. And all the three are absent, then DN point group may be present. Now, in case of Cn doesn't perpendicular to NC2, in that case, we have to go for the Cn, CNH, CNV, and CNV. If sigma is present, then point group may be CNH, sigma V, then DNH, CNV, sigma D, then CND, and all the three are absent, then point group can be assigned as Cn. So, dear participant, with the help of this chart, we can assign our point group to the molecules. So first molecule is hydrogen. First molecule is hydrogen. Now, in case of the hydrogen, we know that hydrogen is a linear and C infinite B or D infinite H point group may be present. So, in case of hydrogen, C infinite B or D infinite H point group may be present. But in this molecule, this is the main principal axis, and this main principal axis is perpendicular to the plane. It means this plane is sigma H. It means point group is D infinite H. So point group for the hydrogen molecule is D infinite H. Second molecule, this is carbon dioxide molecule. In case of the carbon dioxide molecule is a linear. It means we have to go for the C infinite B or D infinite H point group may be present. But in case of the carbon dioxide molecule, this plane is perpendicular to the main principal axis. It means sigma H is present. It means point group is D infinite H. Next molecule is hydrochloric acid. Now, in case of the hydrochloric acid, this is the main principal axis, and this main principal axis is parallel to main principal axis, and the plane is parallel to main principal axis. So this molecule is a linear. So we have to go for the C infinite V and D infinite H point group may be present. Now, here this plane is parallel to main principal axis. It means sigma V is present. So point group is C infinite V. Now, in case of carbon monoxide, again, the plane is parallel to main principal axis. So, this plane is a sigma V. This is linear molecule. It means C infinite V or D infinite H point group multiplication. But here sigma V is present. It means point group is C infinite V. Next example is pipette. Now, in case of the pipette is a linear. It means C infinite V or D infinite H point group may be present. But the plane of pipette is parallel to main principal axis. It means sigma V is present. It means point group is C infinite V. Crucible, cap, man, these are the examples of C infinite V point groups. So remember that pipette, cap, man, crucible, these are the examples of C infinite V point group. Next one is methane molecule. Now we know that methane is a tetrahydral. The shape of the methane is tetrahydral, and this molecule consists E, (4C3), sigma D, and so on. Symmetry elements are present. So let us start. Is it linear or non-linear? Is a molecule linear or non-linear? This is non-linear. It means C infinite V and D infinite H point groups are absent. So non-linear. So next, we have to go for the next question. Any multiple higher order axis are present? Now we know that the meaning of multiple higher order 3C3 is the minimum criteria to be a multiple higher order. It means multiple higher order axis. This molecule consists 4C3. Higher order is 3 and multiple is 4. So this is the minimum criteria 3C3, and our methane molecule consists 4C3. So it is a multiple higher order axis are present in case of the ammonia molecule. In case of the methane molecules, it means TD or TD, OH or IN molecule may be point group may be present. Now, this molecule also consists sigma D, or the shape of this molecule is tetrahydral. It means this molecule is a sigma D. Sigma D is present. It means point group is TD. TD means tetrahydral, or we can say shape of the methane molecule is a tetrahydral. So TD point group is present. Okay, so another example is Sf6 molecule. Now the shape of the Sf6 molecule is octahedral. It means this is the main principal axis as a C4, E, 3C4, C4 is perpendicular to 4C2 and sigma H. These are the symmetry elements. So first, is it linear or non-linear? Non-linear. Multiple harder? Yes. This molecule consists 3C4. It means multiple harder axes are present in case of the Sf6 molecule. It means point group may be TD, OH, and or IN. But this molecule consists sigma H. It means point group is OH. Point group is OH. Next molecule is heterocium. Hypochlorous acid. And we know that how to generate hypochlorous acid. If we pass chlorine gas through water to generate hypochlorous acid plus hydrochloric acid. Now, in case of the hypochlorous acid, molecules are non-linear. Multiple harder axes are also absent. Any proper improper axis, proper and improper axis are also absent. It means we have to go for the C1, CS, or CI option. So here, this is planar molecule. It means point group is CS. Okay, so point group is CS. Next molecule is this is trans difluoroethane molecule. According to the fission projection diagram, this carbon fluorine bond is opposite to this carbon fluorine bond. This carbon fluorine bond is opposite to this carbon fluorine bond, and this carbon hydrogen bond is opposite to this carbon hydrogen bonds. So this is the examples of trans difluoroethane, and this molecule is a non-linear. Multiple harder axes are also absent. Any proper improper axes are also absent. It means we have to go for these options C1, CS, and CI. But here I is present. Center of symmetry is present in this molecule. So point group is CI. This is the different substituted methane derivative. X, Y, and Z. X, Y, and Z are the different groups. Then this molecule is non-linear. Multiple harder axes are also absent. Proper improper axes are also absent. Then we have to go for this option C1, CS, or CA. But here sigma H and I both are absent. It means point group is C1. Point group is C1. Next molecule is water molecule. In case of water molecule, this is the imaginary axis. This molecule consists E C2 sigma V exchange sigma V YZ symmetry elements. Okay, so let us start. Molecule is a linear, non-linear, non-linear. Multiple harder axis, no. Multiple harder axis are absent. Why? Water molecule consists only one C2. It means multiple hardware axes are absent. Then we have to go for the any proper proper axis there. C2 proper axis is present in the water molecule. So we have to go for the yes. Then in case of the proper axis, we have to go for the C2 perpendicular to and C2. It means C2 is perpendicular to two C2s. No. Water molecule consists only one C2. So C2 doesn't perpendicular to two C2s. It means we have to go for the C option. It should be known. Okay. So dear participants, we have to go for the any proper or improper axis of rotation. Yes, proper axis. In case of the proper axis, Cn doesn't Cn perpendicular to NC and means order of axis. So in case of water molecule, order of axis is equal to 2. So C2 perpendicular to two C2s. No, C2 doesn't perpendicular to two C2s. It means we have to go for the C option. Here n is equal to 2. And water molecule consists two vertical planes. It means sigma V is present. It means point group is C2V. Point group is C2V. So here n is equal to 2. Why n is equal to 2? Order of axis for water molecule is 2. Now next molecule is ammonia molecule. We know that the shape of the ammonia molecule is pyramidal. Shape of the ammonia molecule is pyramidal. This molecule consists in 2C3. It means C3 plus and C3 minus and 3 sigma V. All the three planes are the vertical planes and all are the sigma V y z. Okay. This molecule is a nonlinear. Multiple harder axes are also absent. Any proper or improper axis? Yes, proper axes are there. C3 plus and C3 minus. But here C3 doesn't perpendicular to 3 C2s. It means you have to go for the C option. So C3, C3H, C3V or C3D point group may be present. But here sigma V, 3 sigma V, 3 vertical planes are present. It means C3 V point group is present. So point group for the ammonia molecule is C3V. Next molecule is BF3 molecule. This is planar molecule. BF3 molecule consists in 2C3 and C3 is perpendicular to 3C2 and sigma H. Okay. This is the main principal axis. And these three are the subsidiary planes. And the subsidiary planes are the, these are the subsidiary axes. And all the three are C2s. And this plane is perpendicular to the main principal axis. So this plane is sigma H. Molecule is a nonlinear. Multiple order axes are absent. Proper axis, yes. Here, two C3s are present. It means we have to go for the C3 is perpendicular to 3 C2s. It means you have to go for this option, D options. It means D3, D3H, D3V, or D3D point group penetration. So here, sigma H is present. It means point group can be assigned as D3H. Okay, so first, C3 is perpendicular to 3C2. Here, order of x is equal to 3. It means n is equal to 3. So we have to go for the D3, D3H, D3V, or D3. But here, sigma H is present. It means point group is D3H. Next molecule is benzene molecule. Now, in case of the benzene molecule, this molecule consists in 2C6. C6 is perpendicular to 6C2 and sigma H point. Sigma H symmetry elements. Now, this molecule is a linear, non-linear. Multiple hydroxes are also option. It means you have to go for the any proper, improper. Yes, proper axes are present. Then we have to go for this option. Here we have to go for the C6 is perpendicular to 6C2. Yes. So we have to go for the B option. So point group may be D6H, D6, D6V, or D6D. But here, sigma H is present. It means point group is D6H. This is PF5 molecule, phosphorus pentafluoride. The shape of this molecule is trigonal bipyramid. This molecule consists in C3. C3 is perpendicular to 3C2 and sigma H. Molecule is a non-linear. It means C infinitely, D infinite H point groups are absent. Any multiple harder axis? Multiple harder axis are also absent. Any proper axis? Yes. C3 proper axis is present. So we have to go for the C3 is perpendicular to 3C2s. Yes. Then we have to go for the D options. D3, D3H, D3V, or D3D. So point group is D3H. Sigma H is present. It means point group is D3H. Next molecule is this is trans-dichloroethylene. This molecule consists E, C2, sigma H, and I-symmetry elements. Okay, first, this molecule is a linear or non-linear? Non-linear. It means C infinite V and D infinite H point groups may be absent. Multiple hydroxes are absent. It means TDOH IN point groups are absent. Then we have to go for the any proper, yes, proper axis. Which proper axis? Only one C2 is there. So we have to go for the C2 doesn't perpendicular to two C2s in case of the trans-dichloroethylene. It means we have to go for the C option. In case of C option, C2, C2H, C2V, or C2D. Why? Trans-dichloroethylene molecule consists two order of axis is equal to 2. It means point group may be C2, C2H, C2V, or C2D. But here sigma H is present. It means point group is C2H. Next molecule is NaCN4 minus 2 complex. And the shape of this NaCN4 minus 2 is a planar. This is square planar. It means this molecule consists E. C4 is the main principal axis. C4 is perpendicular to 4C2 and sigma H. So molecule is nonlinear, multiple Haro axis are action. C4 proper axis is patient. It means we have to go for the C4 is perpendicular to 4C2. Yes. So we have to go for the D option. It means D4, D4H, D4V, or D4D. But in case of the NaCN4 minus 2 complex, sigma H is patient. It means point group is D4H. This is non-planar hydrogen peroxide. In case of the trans hydrogen peroxide, this is non-planar hydrogen peroxide or cis hydrogen peroxide. This molecule consists E and only C2 and 2 sigma B. So from here, we have to go for the one proper axis. C2 is there. So C2 is perpendicular to 2 C2s. No, we have to go for this C option. It means C2, C2H, C2V, or C2D. But here, 2 sigma V are present. So point group is C2V. Point group is C2V. This is known as iron pentachloride, pentacarbonate. Now this molecule consists E, C3. C3 is perpendicular to 3C2 and sigma H. So we have to go for this option. C3 is perpendicular to 3C2, yes. So we have to go for the D option. But here, sigma H is present. It means point group is D3H. Point group is D3H. Another example is the boric acid. In case of the boric acid, E, C3, and sigma H is patient. So we have to go for the molecule is linear, non-linear. Multiple hydroxes are also option. Then we have to go for the any proper proper axis. Only one proper axis there, C3. So we have to go for the C option only. So C3, C3H, C3V, or C3D point group multiplication. But here, C3 is present and sigma H is present. It means point group is C3H. So dear participants, with the help of this chart, we can assign a point group to the different molecules. I think you learn very well from this chart. Thank you, dear participants, for listening me very silently. And I am also thankful to the director of the HRDC of the Gujarat University, Professor Dr. Joshi sir, for giving me opportunity to take a lectures. I'm also thankful to Dr. Dilip Vasavasha for giving me opportunity to take the lectures in the refresher course. So thank you very much, sir. So thank you once again to dear participants. Thank you.
Thank you very much, sir. It was very nice and informative session for all. Thank you very much once again.